on. How about now? Is that better? A little bit better? Okay. Okay, so just to remind you, I went through this very briefly the last time, even though I'm charged with not talking about oscillation physics. There's always a little bit of oscillations physics. We've woven into all aspects of neutrinos pretty much. And so this is the three-flavor paradigm where you have a mixing matrix that connects the mass and the flavor states, and these are the parameters of nature that we're after in the three-flavor picture. And the masses can be arranged either in the normal or the inverted ordering or hierarchy. And just to remind you that the oscillation expressions coming from this three-flavor picture are involve only the squares of the differences of the masses. And they do not tell you anything about the mass scale. You get the same oscillation probabilities regardless of the absolute mass scale of the three neutrinos. So this entire pattern here can scale up and down in absolute mass, and you'll get exactly the same oscillation phenomenology. And what that means is that we've made this tremendous progress in oscillation parameter space with these different sectors of oscillation. This is the many orders of magnitude of delta m squared and mixing angle in two-flavor approximations. And we're now squeezing the parameters down to very precise measurements. There's still some of the unknowns of mass ordering and CP by Levy phase. But in spite of all this new knowledge, we still can't learn about the absolute mass scale by neutrino oscillation experiments alone. And you might ask, well, how can we learn about that? In fact, there's two approaches, and one of them I'm going to only mention very briefly, and this is cosmology. There are many observables in cosmology. There's a lot of data now from many different sources, from cosmic microwave background, from looking at large-scale structure, looking at icy supernovae, weak lensing. There are many observables that all go into a big pot of cosmological fits. And from this information, collectively, one can infer the sum of the neutrino masses, since that affects all of these observables in a fairly complicated way. And here's a plot here. This is the sum masses versus the lightest neutrino mass, where here, if the neutrinos are, if it's the inverted ordering, there's a larger sum of the masses compared to normal. And if you come up in this regime where the lightest mass is relatively large, then that is what's called a quasi-degenerate regime, where you still have the mass square differences measured in the oscillation experiments, but the masses are relatively all close to each other. So those are actually kind of the three possibilities: inverted ordering, normal ordering, where actually if you're down here, it's legitimate to call it a hierarchy. If you're up here, the masses are all degenerate. They still have an ordering, but they may all be close to each other. And the information you get from cosmology is on the sum of the masses, basically on this axis. And this is a slide that I stole from a talk at the recent neutrino meeting in Heidelberg, which had a nice summary of the information on neutrino mass from cosmology using many different observables. And you get different fits depending on what particular information you put in, that you throw into your pot and do your fit. And you get, the more parameters you allow to be free, the weaker your limits are, which makes sense. And so this is the summary here, is that depending on the particular assumptions you put into your fit with the cosmological data, you can get sum of masses down to as little as 120 million electron volts. But these limits loosen if you change your assumptions. So there's model dependence there, and at this point, cosmology really needs the input from the neutrino mass. If you have a terrestrial experiment that measures an absolute mass scale, that is a tremendous new constraint that will allow extraction of different cosmological parameters from the cosmological data. So this is sort of my personal view also, is that cosmology is more of a consumer than a producer for neutrino mass, although some people would argue with me about that. So how do you actually measure the neutrino mass terrestrially? Well, we classic method is kinematically. In fact, this is really the same way that we originally inferred the presence of neutrinos at all, is that there's missing energy in a spectrum. And if you actually want to figure out how much of that missing energy is the rest mass of the neutrino, what you can do is you can zoom in on the end of a beta decay spectrum and look for a small distortion. Because right at the end point, the maximum possible electron energy you get from this three-body decay is reduced if some of the energy goes into rest mass, is taken away by the rest mass of the neutrino. And so the signature of non-zero neutrino rest mass is a distortion at the end of this spectrum. So that's kind of the generic approach for getting an absolute neutrino mass in the lab. And one of the best beta decays for going after this, because of the features of it's a simple nucleus, it's a low Q value where you have a large effect from neutrino mass, and it's a reasonable lifetime, is actually to use tritium. And if you work out in detail what the spectral shape looks like, this is the differential electron spectral shape, you can see in here there's the effect from the neutrino mass, which goes in there. But in fact, remember, neutrinos they don't have a single mass. We are in a three-flavor picture. We have three different neutrino masses, and the amount that they contribute to the spectrum depends on the mixing parameters. So the oscillations, the mixing, all goes in there. And so the better you know the flavor mixing parameters, the better you can extract information. And so here, this is a picture of the tritium spectra here. This here is a zoom in, and you can see right at the end point, this is where the effect you would get from a 1 eV per c squared neutrino mass compared to massless neutrino. And you can see it's really only a tiny fraction of the decays where you would actually be able to see this effect. And so in order to measure this, you need huge statistics, you need lots and lots of tritium decays, and you also need energy resolution to be able to map out the shape of the end of that spectrum. And there are several approaches to this. There's Catrin, which I'm going to say a little more about in a bit, which is an evolution of previous experiments. There's thermal calorimetry, which made use of rhenium. I believe this is not really not being pursued further because it's proven hard to scale up. But there are other ideas for the future to go beyond Catrin. One involves the electron capture decay of holmium. I'll say a little bit more about that. And then there's an idea called Project 8, which makes use of a different way of measuring the energy in the spectrum. Just here's some history of tritium beta decay spectroscopy limits on neutrino mass. In fact, some of them were not exactly limits. There's been a bit of going up and down. But the current best limits so far are from the Mainz and Troitz spectrometers here. And these were, the last two of these made use of what's known as a MAC-E filter. Magnetic adiabatic collimation with electrostatic filter is what that stands for. And here the idea is that you have an area with tritium on it. You want a thin source. It's really important to be able to measure the spectrum very precisely. And so you don't want to have the decays such that the electrons have to move through a lot of material, and so you want to have a thin, large area source. And what this does for you is it will take the emission from an area over 2 pi and then spread it out into a region where you have an electric field on it that will remove all energies less than a certain value. And then you count the amount, it's an integrating spectrometer, so you count the decays that happen over a specified value, and you can move that threshold so you can integrate as a function of energy. So it's basically an integral spectrometer. This is very challenging. You need a very large detector, and Mainz and Troitz were both instances of similar kinds of instrumentation. The current best limits, which is already some time, approximately a decade ago, the best limit on neutrino mass is a bit less than 2 eV on the absolute scale for neutrino mass, for tritium decay. The current instance of spectrometer, I think the only one doing it in this way now, and it's kind of now I think at the end of the technological path, is the Katrin experiment in Germany going after sub-EV neutrino mass measurements with tritium decay, and this is a fabulous thing. I saw it in person this summer after the neutrino meeting, or actually during the neutrino meeting, during the excursion. It's a very beautiful and sophisticated device, and there's this enormous spectrometer here, vacuum filter thing there. So this is the beam line with the tritium. This is where the electric field is applied, and then the detector is over here. 75 meters long. This is a famous picture you've probably seen of the spectrometer navigating through a small village to get to its get to Karlsruhe, where it's installed now. This experiment has now achieved first tritium injection several months ago, which is really fantastic, and is now taking data. This is a picture I took myself on my cell phone. This entire thing is at will be at high voltage. It wasn't at the time, but it's really a very impressive device. And first results are expected in 2019. It's really, really exciting. How well will this do? So here's the plot here of mass limit as a function of time. These are the current Mainz and Freud experiments, and this is the projection for Katrin. The aim is to get to be sensitive down to approximately 0.2 EV. Okay, so here's another approach, which I think currently isn't as sensitive, but it's an interesting thing for a future direction, is making use of an electron capture decay in holmium-163. This is a decay where you have a hapless innocent electron that gets sucked into the nucleus and combines with a proton to make a neutron. And the subsequent de-excitation energy you can observe. And the effect of neutrino mass on the endpoint is similar. This is a distortion you expect in the endpoint. The maximum energy that you could see is affected by the neutrino mass. So the idea there is to do a very precise spectroscopy on the endpoint of holmium. And there's some very interesting novel technology under development to try to observe this spectrum using low temperature microcalorimeters. You need to have very sensitive temperature sensors. You're basically measuring the energy via the heat in the material. And there's different approaches for doing that. They're using superconducting transition sensors and magnetization for magnetic material, so-called NMCs. And these are very challenging. There are many detector performance issues. You have to worry about how to get your source onto there and make a pure background and actually theoretical systematics as well. So this is an interesting development area. And here's another idea, which is a bit orthogonal and actually a very cute idea, less than 10 years old, about 10 years old now. And the idea here is to use cyclotron radiation to measure the data spectrum. Instead of actually grabbing the electrons and recording their energy, instead you put electrons, as the electrons are emitted from the decay in a magnetic field, and they circle around via cyclotron, in a cyclotron radius and cyclotron motion, and the frequency, they radiate, and the frequency of that radiation maps to the energy. And so if you can measure the frequency of the spectrum, you can infer what the electron initial energy spectrum is. So this is a very clever idea. The potential advantage to bring that beyond the Katrin limit is because you can actually potentially use atomic tritium. One of the limitations for the Katrin method is you use molecular tritium, where you have energy that can get sloshed around inside the molecular orbitals, which gives you an uncertainty. If you have an atom of tritium, those uncertainties are not present. And so that's the potential promise of this technique. And there's a collaboration called Project 8, which has been pursuing this, and they've got a plan for various different stages of improved instrumentation. And their current prototype, they've actually demonstrated observation of cyclotron radiation for single electrons, and they've also looked at krypton as well. So this seems to be on track and promising. Still a ways to go in R&D, but very interesting. Okay, so that was absolutely different question, which is connected to neutrino mass, but it's actually maybe one of the biggest questions in neutrino physics, which is the question of whether neutrinos are Majorana states or Dirac states. And neutrinos are Majorana. What that means is that the neutrino is the same as its antiparticle, and there you have basically two states. You have a left and right-handed state connected by Lorentz and CP. And you can also have four states if it's a Dirac neutrino, which is maybe a more standard kind of thing, where you have you can go from left-handed to right-handed with a Lorentz boost, and CP would take you from neutrinos to antineutrinos, but it's effectively four different states. And which of these is true, which truly describes neutrinos, is important for how you write down the Lagrangian for describing neutrino mass. It also has many other theoretical implications. If you want to use the seesaw mechanism, you need Majorana neutrinos. There's also implications for leptogenesis and so on. So this is a huge question that would have very important implications if you can answer. And really, the only plausible experimental way of getting after this question is neutrinoless double beta decay, which is a very rare process that happens and can only happen modulo crazy theoretical things, but it can only happen if neutrinos are Majorana particles. And this is what the decay looks like. Here, I'm going this way. You have a nucleus, which here you have an exchange of a virtual neutrino, and you can only have an inner line like this if neutrinos are the same as their antiparticles. The output is 2 electrons, so it's a double beta decay. And most of the time, this kind of interaction is energetically forbidden. And if it isn't, might also be completely swamped by other decays, by regular old single beta decay, also alpha decay. So if you actually want to search for this very rare process, which is very rare because neutrinos have very, very small mass, you need to have the right isotope. And there are, fortunately, in nature, some isotopes that undergo this process. And here's one example. This is xenon-136, which here's the energy diagram here for A is equal to 136. This is stable, energetically stable against regular old beta decay, and so you would have hope of seeing a very rare decay that isn't swamped by regular beta decays. And here you can have this double beta decay where you create actually two electrons. Here's a table that I stole from Georgia Grada of candidate nuclei that have reasonable Q values. And so these are the, if you go through the table of isotopes and look for the right properties, this is what you will come up with. This is the Q value, which is important because it relates to your observability of your signal. You want to have generally a large Q value, since that's more energy in the detector and easier to see. So these are typically around, these are above 2 MeV, which is not a crazy thing to look for experimentally. This is the natural abundance. These are all occur in nature, but at low abundances typically. You can see the highest one here is actually tellurium, which is 34%, but that's an anomaly. Most of these are at the few to maybe 10% level. So these are isotopes that you can find in nature, but you have to enrich your isotope to have a reasonable amount of this isotope. And that can be quite expensive. So here's the experimental strategy. All of these isotopes will undergo regular beta decay, regular 2-neutrino beta decay, as well as exotic neutrino-less double beta decay. And so this here is, and that will also tend to be rare, but it's observable. It has been observed in many isotopes now. And so what you get from a regular standard model 2 beta decay, where your final state has neutrinos in it, so it's a multi-particle final state, you get a smooth expected spectrum of electrons coming out. But what you get for 0 neutrino-less double beta decay, so this is no neutrinos out, you get only the 2 electrons. What you expect here kinematically is a sharp peak in energy. And so this is the signature, is a sharp peak in energy for 2 electrons at the end of a spectrum of regular standard model 2 neutrino double beta decay. And so here's an expression for the observed half-life here from the standard model, assuming Majorana neutrinos, is you have here a factor that is kinematic, that is the phase space. You have a matrix element, which tells you about the overlap of the initial and final nuclei, that their details of the nuclei, of the actual nuclear physics, nuclear wave functions, that actually matters for this, and that can be very different for different nuclei. And then you have the part with the underlying physics in it. This is the effective mass of the, it's called the effective mass, beta beta squared, and here, this is the weighted sum of the individual neutrino masses of the 3 states weighted by the appropriate matrix elements. So here the mixing parameters go there as well, because what you have is a superposition of mass states, and the oscillation matrix tells you what the superposition is. And so the effective mass depends also on oscillations, it depends on the mixing matrix parameters. Okay, so here is now the diagram. This is what neutrino double beta decay people have on their t-shirts. This is kind of the figure of merit sort of plot, where on this axis here is the minimum mass, and on this axis is that effective m beta beta that I just defined. And here's the definition of it again as an equation. So and it depends on the mixing parameters. And so here, depending on the actual values of the absolute masses, of the masses of the absolute mass states, then you get different, nature will choose points in this region according to the absolute masses and according to the mixing parameters. And so if neutrinos are Majorana, so that statement I just made was only if neutrinos are Majorana, then the measurement of this parameter, this is an observable, will fall in one of these ranges as a function of the minimum mass of one of the neutrino mass states. And the size of the regions depends on the uncertainties of these matrix elements here. And if we knew them perfectly, they would squish down to thin lines. We don't know them perfectly right now. There are also Majorana phases in the mixing matrix that are not observable in oscillation experiments that also contribute to the width of these regions here. And so if the hierarchy is inverted, then nature will choose, you will measure something that falls in this region here. It's basically you've got more absolute mass there, so your effective mass will be larger, so you'll be in this band here somewhere. If the hierarchy is normal, so kind of have less mass in the 3 states, you will come into this, you will arrive in this region here, and then there's an overlap region where the masses are quasi-degenerate. And so here, normal ordering will, it's like you've got one big one and 2 little ones, you've kind of got less mass there is this region. That's the inverted ordering, you've got two fat ones, one little one. Quasi-degenerate is where they're pretty much all similar, but the mass ordering is according to is either inverted, it's still either inverted or normal. Now the absolute mass scale, such as what you would get from Catherine, constrains in from the right to the left. So if you know the absolute mass scale is very small, you would rule out the upper part of the plot. Let me make a comment on nuclear matrix elements. This is actually a big deal for neutrinos double beta decay. That comes into the half-life, the inverse half-life here, and it depends on the specific nature of the nuclei in the initial and final states. There is quite a range of values for the different nuclei, and there's also a lot of uncertainty in the theory even for a given nucleus. And so this is an example. This is from a last year survey of knowledge of nuclear matrix elements for neutrinos double beta decay, And each of these points is for a given A value that corresponds to a different nuclear physics calculation, and you can see that there's a variation over an order of magnitude. So this is a big uncertainty in neutrinoless level beta decay. You can have, if you have a small matrix element, just from the nuclear physics, just that particular nucleus doesn't like to change to the final state. You can have a suppressed suppressed neutrinoless level beta decay rate by quite a bit. But we don't know exactly how much right now, but there's a lot of theoretical work underway to try to improve the estimates here. And this actually underscores that if you want to measure neutrinoless level beta decay, it's a good idea to have more than one isotope because the uncertainties on the nuclear matrix elements are quite large. So here, the way one can report an experimental result on this kind of plot is to quote a range, and this is now kind of the conventional thing, is if you measure a particular, if you have a limit on a half-life, or if you have a measurement of a half-life, you would put a range here that corresponds to different matrix elements that give you a range of different effective masses. And so a measurement or limit will correspond to a band on this kind of plot. I can mention briefly, there was some years ago, now almost 15 years ago, a controversial claim by the Heidelberg-Moscow experiment, this is known as the KK claim, that claimed that an observation in neutrinoless level beta decay in germanium corresponding to effective mass of about 440 millielectron volts. So that would be on this plot somewhere up here. And over the last decade or so, there's been, the goal has been to attain sensitivity better than this claim in order to confirm it or to rule it out. And as I'll show you in a bit, we're actually now pretty much below that claim. The next goal, given that we're now pretty much below that claim, is to actually get below this inverted hierarchy region. And so let me just make some comments here. That if you measure a neutrinoless double beta decay signal in either of these regions, and the direct mass limit is sufficiently low, this is actually not very likely to happen, but if that were true, then in principle you could determine the hierarchy. However, it's not very likely we're going to get absolute mass limits less than 0.01 eV in the near future. The thing that is much more likely to happen is that the hierarchy will be determined first by long baseline or perhaps other experiments, so perhaps a supernova or something like that. And actually, currently, the hints from long baseline experiments are that the hierarchy is normal. This is only kind of 2 sigma-ish hints, but it seems it's looking more like normal than inverted. And so what that will do is it will constrain, if neutrinos are Majorana, where the signal could be. And if it is inverted, in spite of the long baseline hints, we are in a heavenly situation. If it's inverted and neutrinos are Majorana, then if we can just get below this inverted hierarchy region with neutrinoless double beta decay experiments, we will see it if neutrinos are Majorana and the hierarchy is inverted. So that would be awesome. Or if you know the hierarchy is inverted and you measure a limit below that region, that would be very good evidence, assuming nature is not diabolical, that would be very good evidence that neutrinos are not Majorana. So that would also be a very, very interesting result. However, nature isn't necessarily not diabolical. It's a negative. You can also say, now it also may be if the hierarchy is known independently to be normal, which is sort of where we're going now, then life may be pretty hard. If you know the mass scale is small, then it may be very, very difficult to get to this region here, because we know then the signal would be in this region if the mass scale is large. But the absolute mass scale, if the mass scale is small, then your life as a neutrinos double beta decay experimentalist is going to be very, very miserable. However, and in fact, it could even be really miserable. It could be, it could be this pit of despair if nature has actually chosen these parameters down here. And so, nature, we don't know that nature isn't diabolical. But we do still have hope now. we hope that Katrin here, if it actually manages to show that the absolute mass scale is high, if there's actually a signal from Katrin, and we know that the mass scale of neutrinos is maybe half an eV or something like that, that will mean that we're in a quasi-degenerate regime, and that in fact it may be a reasonable thing to hope for to see neutrinos level beta decay out in this region over here. And so we still have hope alive. Okay, so let me say a little bit about experimental sensitivities and experimental approaches. I'm not going to go through all of the different experiments in detail, I just want to outline the kind of general approaches. So the half-life limit that you would get from taking a chunk of neutrinos level beta decay isotope and looking at it for a long time and looking at the endpoint here is given by this expression. So it's proportional to the detection efficiency, you want that to be high. It's proportional to the number of source atoms that you have, to the size of the chunk of matter that you have. It's proportional to the time that you can watch it for. Here in the denominator is the upper limit for expectation of E background events if you have a region of interest at the end of the spectrum of width delta E. Okay, so this is a measure of the background that you expect within your region of interest, your ROI, your signal region. So there are different approaches, and you can use more than one of them at the same time. So one approach is to go after the numerator, is to try to observe as much isotope as you possibly can for as long as you can with as high efficiency as you can. So there you want to have lots and lots of candidate isotope. Just to give you a sense of the scale of how much you need, if you want to see a lifetime of 10 to the 26 years, that would correspond to about 50 EV, which is in the inverted milli-EV, in the inverted hierarchy region, you need about 1 ton of material to get 1 count per year. Okay, so you need quite large amounts of material because it's very rare case. And so, therefore, you also want to have an isotope that has a high natural abundance, which usually means that, you could use natural isotope, or you could enrich it, and if it has high natural abundance, it's usually cheaper to enrich it. You can also go after the denominator. You can zoom in on this region, and you want to be able to pick your events in a really narrow region to avoid background from standard model to neutrino delta beta decay, which is kind of a friendly fire there. That will, if you have poor resolution, will leak into your signal region. You also want to have a high Q value, usually, because that usually makes it easier to select signal from just ordinary, boring background, radioactivity, and so on. You also need, in general, to reduce all your other backgrounds. These are very rare decays, and it's very hard to get rid of all kinds of other stuff that can mess you up, cause rays, radioactivity, detector noise, all those kind of things. And so you generally need to have a very clean detector, which actually also usually needs to be underground to get away from cosmogenics. And so here, this is my personal characterization of the different strategies you can use to either go after the numerator or the denominator, or both of these. So on the left here is what I would call the brute force approach, which is if you can focus on getting a huge amount of material, you often might have to sacrifice resolution. It's hard to instrument a very large detector to get very good energy resolution. This goes back to the question somebody asked yesterday, is why are your thresholds so high for the neutrino detectors? It's hard to gather energy from a huge volume and measure it. And so you often have to sacrifice resolution if you want a very large detector. And it can be expensive, of course, also to get very large amounts of material. But it's an approach. Another approach is what I call the peak squeezer approach. This is where you focus on the denominator by trying to get the best possible resolution so that your signal is you're only looking at a very tiny range where you expect your very sharp signal to be, and you reject all the background or the friendly fire outside of that region. And there's many technologies that are good for doing that. And then the other one here is what I call the final state judgment approach. This is where you actually want to try to make the background really very close to zero by actually looking explicitly for a 2-electron final state. So if you have a good enough detector, you can actually see 2 electrons come out of the vertex and actually potentially even track them and use that to project background. There's also other ways of tagging to see the daughter nucleus. If you can identify the specific daughter nucleus coming out, then that is also a tag that you can use to reduce background for neutrinos double beta decay experiments. And of course, these approaches are not exclusive. You can potentially use more than one approach. So let me give you some instances. I'm not going to go through every single neutrinos double beta decay experiment, but I can give you some examples of these different approaches. So for the brute force approach, some particular instances are Camland Zen, which is in Japan, which uses the Camland reactor experiment scintillator and has a bag of xenon 136 double beta decay isotope inside it, and that's really a really quite large, hundreds of kilogram size scale material that they can observe inside the Camland detector. So that is one approach. Another one is SNOW Plus, which is also a former neutrino SNOW experiment, which is now being filled with scintillator. I think it has water in it right now. I talked about that yesterday in the context of supernova neutrinos, so it's actually a great supernova neutrino detector. But its current mission in life is to look for neutrinos double beta decay with